Why do we need these? What it is, it's A times V gives you a scalar times V. What does that actually mean in terms of transformations? What does the A do to the vector V? If you've got that situation, what's it going to do? Yeah, scales a vector, doesn't it? Okay, so if you took a vector, if you took something like this, and then if you got V down here, okay, all A will do is move it along there, yeah? A will just move it along there, either in the same direction or exactly opposite. It will not move it, it will not divert it, it will not move it up here. Okay, it's not going to rotate it in any way or reflect it or anything. It's going to move it along there. This is what we've got eigenvalues, eigenvectors, is where AV is equal, it just scales and multiplies the vector V. That's what it does, AV, okay? When you have that, that's when you've got eigenvalues, eigenvectors. And then you might ask, well, where do we actually need this? Well, one great example, if you look, I mean, in the final year, you have an option of doing what we call an investigation, okay? And you can do an investigation in, Google ranking. If you do a Google ranking, the way Google ranks, like I said, if I enter Patrick Harrison, University of Hertfordshire, how does it know which page to put first? Which pages are relevant, and so on. Okay, and the way that is done is also to do with eigenvalues, eigenvectors. It's a very large matrix, but it's got everything to do with eigenvalues and eigenvectors. I guarantee you that. So this is where it's used. And if you look at singular value decomposition, which we don't do, singular value decomposition, the way if your email signature contains a photograph of you or an image of you, okay, the way it changes from a very large matrix, a very large, 1,000 by 1,000 matrix, whatever it may be, into a matrix which has got much smaller rank. What's the advantage of having a smaller rank matrix? Less data. How would it help you anyway? Less data. You don't want to lose any of the data, of course. You want to pick that picture up. So if I took a picture of you now, I want to see that picture there as well. So what do you gain? What does it mean by less data? It's not going to show all your face. Sorry. Who's speaking? Where's the mouth? I can't see. Yeah, what do you say? Yeah, computationally it's more efficient, isn't it? Yeah, computationally more efficient. So SVD is the last chapter, last section of this, but we don't do that. Anyway, let's do an example. So let's do this example here. So you've got A times this. Okay. Like I say, this eigenvalues are very useful indeed. And you'll find that there's going to be two sections of a diagonal. We're going to convert a matrix like this into a diagonal matrix. So then you can find, with a diagonal matrix, you can find things like, diagonal matrices are good. They're easy to deal with. They're much easier to deal with, diagonal matrices are much easier to deal with than non-diagonal matrices. Then if I ask you to find A to the power 10, now at the moment, the only tool you have is A times A times A times A times A times A, and 10 copies. You don't want to do that. I don't want to do that. Bound to get it wrong, aren't we? Okay. With eigenvalues, eigenvectors, you'll find it so much easier, a lot easier. Okay, convert it into a diagonal matrix, and you find the power of that, and then you can convert this back. Anyway, let's find this. A times matrix A times V gives me what? I multiply this out. What do I get? AV is equal to what? 4 minus 2, 1, 1, 2, 1. Yeah? Okay, what do I get if I multiply this matrix out? Come on. Come on, you're not going to tell me you don't know how to multiply 2. What do we get? Yep.
So you get 6.
Yeah, 4 times 2 is 8, minus 2 gives you 6. Yep, 6.
And you get 3.
3, yeah. How else can I write the vector 6, 3?
Then you can take out 3.
Factor of 3, 3, 2, 1. And what do you notice about your result? Remember I said, don't learn mathematics the way I learned mathematics. When you get an answer, what's it mean in relation to the question? Much better way of learning mathematics. Okay? Well, let's have someone else, Patrick. Sorry? 3u, yeah, exactly. It's 3 times the initial vector, isn't it? 2, 1, okay? So what you got here is AV is equal to 3v, or whatever AU is equal to. Sorry, it was U, I called it V. So what's the matrix A done to that vector? What's that matrix A? What's it done to that vector V? It's scaled up by a factor, triple it, yeah, hasn't it? Yeah, scale and multiplied it by 3. So you've got U up there, okay? Multiply that by 3 is what AU has done. So what we write this is AU is lambda U, lambda Sylvester. You know that one who I said who was a bit of a psycho. You know, I'll talk more about that this afternoon when we do MT1. Some other, not him, but someone else who was a bit of a psycho as well. Okay, you know. He's the one first introduced, gave us lambda for eigenvalues. He's the first one who came across lambda. Well, that's why he nominated it as lambda. That's why a lot of textbooks, a lot of mathematical literature and engineering and so on, and sciences use lambda for an eigenvalue. You can use t if you want, but you'll see lambda. Well, I better call today. I only got the last 5 minutes. You know, if you look at the videos, I can hear you talking all the time. You answering all the questions. If you look at the videos on Tuesday.
Can you hear me answering all the questions?
Yeah, when I ask questions, it comes up and the